మళ్ళీ ఫస్ట్ నుంచి చెప్పాలి. In this session, I want to discuss in the same concept, in the same chapter 1, in types of switches concept. I want to do small concept, then you go for whatever the concepts I discussed in chapter 1. Based on that, I want to solve some practice questions also. Okay. Say in this, we go for a small concept. If the device is conducting, if any semiconductor device is conducting, how to calculate average conduction losses or average power loss during conduction of semiconductor device. Okay. Calculation of, this is one concept, calculation of okay, average power loss, during conduction of device, during conduction of switch or device, during conduction of device. Okay. How to calculate average power loss during conduction of a devices. Okay. We know that if any device is conducting, if any device is conducting, it is represented or modeled as following, equivalent circuits. Okay. One equivalent representation is, it is represented with on state resistance of R on, at the current is I. Or it may be modeled as on state voltage drop of VD, let the current is I. Or it may be modeled as on state resistance and voltage drop. This is I, this is on state resistance R on, voltage drop is VD. Okay. Now, in this case, if it is represented with only resistance, then how to calculate average power loss? Then average power loss equal to, how to write? Then 1 by T integral 0 to T on I square R on dt. I square R on dt. Shall we write like this? Then average power loss equal to, take this R on is constant, R on into 1 by T integral 0 to T on I square dt. Okay. Then what this formula indicates? What this formula represents? Okay. Then shall we write like this? This R on into I RMS square. Therefore, if it is represented with the equivalent resistance, then to calculate average power loss, that resistance is multiplied with the RMS square, then you can get the average power loss. This is one observation. If any device is represented with equivalent resistance, simply remember like this: to get the average power loss, that on-state resistance is multiplied with the RMS current, RMS square current. Okay. Next, if any device is represented with equivalent voltage drop, or it is represented with some cut-in voltage, then how to calculate average power loss? Then the average power loss equal to P average equal to 1 by T integral 0 to T on. This is Vd into I into dt. Okay. Now you simplify this one. P average equal to Vd is constant now. Vd into 1 by T integral 0 to T on I into dt. Then what this formula indicates? I average. Then average power loss equal to, that is Vd into I average. That means if any semiconductor device during the conduction, if it is represented with the constant voltage drop or cut-in voltage, to calculate average power loss, that voltage is multiplied by average current. It is not a RMS current. Important observation. With respect to resistance, to calculate the power loss, you multiply with RMS current. Okay. With respect to constant voltage drop, with respect to constant voltage, to calculate the average power loss, you multiply with average current. It is not a RMS current. Understood? Okay. Now, if it is given both resistance and voltage drop, then how to calculate average power loss, you tell me? Yes. Average power loss equal to, then it is a combination of both resistance and constant voltage is given. With respect to resistance, how to calculate power loss? That is IRMS square into R on plus. With respect to voltage drop, constant voltage, how to calculate average power loss? Vd into I average. Like this, you can calculate the average power loss based on the equivalent representation. With respect to resistance, with respect to constant, and combination of these two. Okay. This knowledge is important to calculate the average power loss in any power semiconductor device during the conduction state. Okay. These three important observations. If it is only resistance, if it is only voltage drop, by combination, how to calculate the average power loss. Understood? Okay. Now, with this knowledge, okay, now we go for different models of questions already framed in various competitive point of view. Then this knowledge is important to solve those questions. Okay. Now go for different models of questions in different topics. Okay. Think you note down this one? I told already. Parallelly note down by listening and note down all these concepts for you. Then here I am solving chapter 1, types of switches concept. Go for some classroom workbook. I think this classroom workbook is available to you. Then in this, the classroom workbook, the types of switches concept, that is chapter 1, that is chapter 1, types of switches concept, then classroom workbook concept that I am giving. Okay. See the topic 1. Under topic 1, calculation of average switching power loss and energy loss. This comes under topic 1 questions. This is topic 1. This topic 1 is which one? That I given calculation of average switching power loss and energy loss. Average switching power loss average switching power loss and energy loss. Under this topic, we are solving some questions. Let us see the first question I given that you will see in workbook. Okay, under this concept, the voltage Vs across and current Is through a semiconductor switch during a turn-on transition are shown in figure. The energy dissipated during the turn-on transition in millijoules is dash. Here there is some characteristics are given. In this characteristics, calculate what is the energy during turn-on transition. Okay. In the first question, this is first one. In topic 1, this is first question. These are the characteristics given. These are the characteristics given. This is the given characteristics. Yes. And this is the voltage across the switch. The voltage across the switch is given like this. This is voltage across the switch. And current through the switch is also given. Current through the switch is also given. This is T and this also T. Then current through the switch is also given. Yes, the current through the switch is given like this. Yes, this is the current through the switch. This is 1 microsecond. This time is given as 1 microsecond, that is T1 time. And this also given as 1 microsecond. Is also given as 1 microsecond, and this current is 50 amperes. These are the given characteristics, and this current is 100 amperes. 100 amperes, and this voltage is given as 600 volts. Okay. Then this is voltage across the switch, and this is current through the switch. Current through the switch. Okay, this is 1 microsecond, this is also 1 microsecond. Then we calculate what is average the energy dissipated during turn-on transition in millijoules. Okay, that means what is the energy, then what is the solution for this problem is, this is first question, what is the solution is, then we calculate energy during turn-on transition. What is the energy dissipated? Energy equal to. Okay. What is the fundamental definition of how to calculate energy? Integral V I dt. This gives the energy. Sorry. This gives the energy. Integral V I dt. Okay. Now see. Here voltage is present but current is not exist. Here we don't have any energy loss. Okay, this is energy loss we are calculating. Energy loss. Next, here voltage is present, current is also present. That's why here energy loss is exist. Here also voltage is present and current is also present. That's why energy loss is exist. Can you tell me? We are calculating energy loss now. In this 1 microsecond of time, in this time, voltage is constant, but current is changing. Yes or no? Voltage is constant, current is changing. Can you write like this? V is constant, integral I dt plus next to 1 microseconds of time, voltage is changing, but current remains constant. Current is constant, then I into integral V dt you write now. Yes? Tell me. In this 1 microseconds of time, what is the voltage? Yes, 600 volts. 600 into. What this indicates? Integration of current. Integration is nothing but area under the curve. In this time, what is the area under the current curve? We can apply that one. Now tell me, what is the area under the current curve? 1 by 2 into, it is triangle, it is one triangle, half BH. 1 by 2. Then what is B? 1 microsecond. 1 into 10 to the power of minus 6. What is H? This is 50 plus 100. 150. Plus. So, okay. During this 1 microseconds of time, current is constant. How much this current? This is 50 amperes, this is 100 amperes. 100 into. What this indicates? Area under the voltage curve. During this time, this voltage curve is also triangle. Then what is the area under the curve? Half. B is how much? 1 microsecond. H is how much? 600. H, sorry. That is area under the curve. H is how much? 600. S, this height is 600 volts. This base is 1 microsecond. Now tell. You simplify this. What do you get? Simplification. Here 600 is common. 600 into 10 to the power of minus 6 is common. Okay. 1 by 2 into 150, 75 plus 1 by 2 into 100, that is 50. S, then how much you get? 600 into 10 to the power of minus 6 into, this is how much? 125 now. S, 125. Yes, 125 into 6 into 10 to the power of minus 4 no? Yes, this is how much? This 125 into 6. 125 into 6. How much you get? This is 125 into 6. Then we get 75 millijoules. This is, you get 750 na? 750 that I written 75 millijoules you can get. And this is the problem. Simple. The question is asked, calculate energy loss. It is not a power loss. Calculate energy loss. In the problem it is mentioned that calculate energy loss. Then that I. In this area voltage is constant, current is changing. That's why kept V is constant, I is changing. In this area, current is constant, V is changing. Kept I is constant, voltage is changing. This is the first problem. The answer is 75 millijoules. Understood. Then go for next question. The second question. The figure shows the voltage across a power semiconductor device and the current through the device during switching transitions. Is the transition a turn on transition or a turn off transition? That is question mark. What is the energy loss during the transition? Here some characteristics are given. In this characteristics, first you identify, is it a turn on transition or turn off transition? In the same question, then what is the energy loss during that transition? First identify type of transition and you calculate what is the energy loss. What are the characteristics? These are the characteristics given. This is the given characteristics. Okay. This is voltage V and this is current I. This is I and this is V, this V comma I. Okay. This time is taken as a T1 time and this is T2 time. Okay. This is T1 time. Understood? Now, what is the solution for this problem? First, I want to identify it is a turn-on transition or turn-off transition. Okay. Now see, current is rising, voltage is falling. That is, in this characteristics, current rising, and voltage is falling. Voltage is falling. Hence, it is which transition? Tell me. It is a turn-on transition. It is turn-on. It indicates that turn-on transition. Current is rising, voltage is falling. Now, what is the average energy loss? Energy loss during turn-on transition. That is integral VI dt. During T1 time, which is constant? Voltage is constant. Shall you write like this? V into I dt plus. During T2 time, which is constant? Current is constant. I into integral V dt. Okay. Then V is constant, that is capital V. What is triangle area under the curve? Half into what is this height? I into T1 plus what is I? That is capital I. What is integral V dt? Area under the curve, half into T2 into what is height for area under the, that is voltage curve na? What is this one? V. Then half VI T1 plus T2. Then it is which transition? Turn-on transition. This is the answer. In the given question, then which option is correct? It is a turn-on transition. Turn-on transition. Half VI T1 plus T2. That's why option A is correct. The solution for this problem is option A is correct. The answer is option A according to in the given question. Understood? This is the, in topic 1, this is the second question. Clear? It's okay? See this. Same model, what I get, where the problems values are substituted. Here we are calculating just the area only. Not, values are not given. Understood? For this area, first voltage constant, current changing. Here current constant, voltage changing. Area under this curve, area under this curve. That I calculate. But first identify it is a turn-on or turn. Current is rising, voltage is falling. That's why it is a turn-on transition. Then go for next question in the same topic. Is it okay? Then question number 3. See that in a semiconductor, the anode current rises linearly from 0 to 100 amperes, that is I1. Whereas anode voltage across device falls linearly from 600 volts to 0. Okay. During its turn on time of 5 microseconds, for a trigger frequency of 100 Hz, find the average power loss. The device is taken as a SCR. Okay, average power loss in a device. Understood? Find the average. It may be SCR or any device it may be given. Find the average power loss in a device. Understood? Okay. It is given like this now. According to problem, first you draw the characteristics. In a semiconductor, the anode current rises linearly from 0 to 100 amperes. That is I1. Let us consider the, according to given problem. First here I am drawing the characteristics. What is the solution for this problem? Okay. According to given statement, I am drawing the characteristics. Anode current is rising 0 to 100 amperes. Rising 0 to 100 amperes. This is 100 amperes. Okay. Then anode voltage is falls linearly from 600 volts to 0. Let this is 600 volts to 0. This time is how much? 5 microseconds it is given. And also given switching frequency. How much switching frequency it is given? The switching frequency is mentioned that 100 Hz. Then calculate average switching power. Calculate average power loss. The characteristics are just like linearly rising and linearly falling. If it is linearly rising and linearly falling, then what is the average power loss that I given now? For linearly rising and linearly falling, the average power loss equal to 1 by 6 VI F into T on. This formula I already given in the concept. Understood? That is 1 by 6. What is the voltage? 600. What is the current? 100 amperes. It is 100 amperes. What is the frequency? 100 Hz. What is the time taken? 5 microseconds. Then how much you can get? This 6. This is cancel out. Then 30 by 6 into 5. 30 by 6. How many watts? 5 watts. This answer. For linearly rising and linearly falling, the average power loss equal to 1 by 6 VI into F into T on. Then what is the average power loss? The average power loss equal to 5 watts. Understood? Okay? Very simple. See the next problem. Fourth one in the same topic. Problem number 4. Question number 4. Okay. During turn on and turn off of a semiconductor device, the voltage and current variations as shown in figure. Determine mean power loss switching at a frequency of 10 kHz. Means turn on and turn off variations are shown in figure. Then you calculate what is the mean power loss at a frequency of 10 kHz. Okay. Then what the characteristics are given? These are the characteristics given in the problem. In the problem itself it is given, this characteristics. These are the characteristics given. Yes. This how much? This is 200 volts. And this is 100 amperes. How much time? 1 microsecond. Okay. This V comma I. The another characteristics it is given. The same problem. Yes. this 100 amperes, and this is 300 volts. Okay, sorry, like this. This is 100 amperes and this is 300 volts. This also V comma I. And this is time. It is given. Understood? Here voltage is falling, current is rising. Yes? That's why it is which transition? Turn on transition. If current is falling, voltage rising na? This is which transition? Turn off transition. Then calculate on state power loss. On state power loss. 1 by 6 VI F into T on. 1 by 6. What is the voltage? 200. What is the current? Okay. 1 by 6. 200 into. What is the current? 100. What is the frequency? Yes, it is given in the problem now. 10 kilohertz. 10 into 10 cube into. What is the on time? How much time? 1 microsecond. 1 into 10 to the power of minus 6. Then what is the on state power loss? You tell me. Yes, the on state power loss is how much you get? On state power loss 1 by 6 into. This is 2. This is 2 into 10 power 8 na. 10 power 8, 2, 4, 5, 8. 10 power 8 into 10 power minus 6. How much you get? This is the on state power loss. 1 by 6 VI into F into T on. 1 by 6. V is how much? 200 volts. S, I is how much? 100 amperes. F is how much? 10 kilohertz. Then T on is how much? 1 microsecond. 1 into 10 to the power of minus 6. Is correct? Then how much you get? This is 10 to 200 by 6 watts. On state power loss. 200 by 6 watts means how many watts? 33.33 watts. This on state power loss. Then similarly you tell me what is the off state power loss? Same formula. Off state power loss. What is the off state power loss? During off state, what is the power loss? What is the off state power loss? Same formula. 1 by 6 VI into F into T off. Okay. 1 by 6 V into. What is the voltage? 300. What is the current? 100. What is the frequency? Yes. Frequency is 10 kilohertz. What is the off state? Off time 2 microseconds. 2 into 10 to the power of minus 6. This is given as 2 in the problem. It is given as 2 microseconds. Okay. Then you simplify this. 1 by 6 into S 3 into 2 6 into 10 to the power of this is 4 5 this is 10 kilohertz na, sorry, 10 cube. 1 by 6 into 10 power 8 into 10 power minus 6. That is 100 watts. Then what is the total power loss? Then total power loss equal to on state power loss plus off state power loss. This is 100 watts and this is how much? 33.33 watts. Then total is 133.33 watts. This is the total power. Yes, this is the fourth question in the workbook, classroom workbook, in the topic 1. You calculate. It is given that it is asked, it is not on state or it is not off state. It is mentioned that power loss. Power loss means you calculate total power loss. Here separately I calculated on state power loss and I calculated off state power loss. then add those two, then we are getting total power loss equal to 133.33 watts. That is the fourth problem in topic 1. Okay. See the next one, the fifth problem, that is the fifth question in topic 1. A power semiconductor switching characteristics as shown in figure. If the mean power loss is limited to 200 watts, the maximum switching rate that can be achieved is dash. A power semiconductor switching characteristics as shown in figure. If the mean power loss is limited to 200 watts, the maximum switching rate that can be achieved is dash. That is. This is question number 5 in topic 1. The characteristics are given like this. Here voltage and current characteristics are separately given. This is voltage falling, that is 120 volts. Okay. Then current is rising. Both turn on and turn off is given. Given that voltage characteristics. Yes, yes. This is only for voltage characteristics. Yes. The voltage is same. This is 40 microseconds. This is 75 microseconds. This is time. Okay. Here voltage is falling. Voltage falling means turn on. Yes, it is turn on. During turn off, voltage is rising. This is turn off. Understood? In the same problem, the characteristics for current is given like this. This is the characteristics given in the same problem. The characteristics of current is given like this. Yes, current is rising up to what current? 80 amperes. Yes, it is 80 amperes. And current is also falling. Current is rising means this is which transition? Turn on. Current is falling means it is which transition? Turn off. Okay. This time is given as how much? 50 microseconds. And this time is given as how much? 60 microseconds. This is T. This voltage characteristics, this is current characteristics. Then you calculate the maximum switching rate that can be achieved. Given that mean power loss, how many watts? Mean power loss equal to 200 watts. Then you calculate maximum switching rate, that is maximum, you calculate maximum switching rate, that is switching frequency, switching rate or frequency is question mark. You calculate maximum switching rate or maximum frequency. Okay. Now, first power loss is given, frequency is asked. Power is nothing but voltage into current. Energy is nothing but voltage into current into time. You calculate energy from the given characteristics. You know the power, you know the energy. Then divide power by energy. Then you get the expression for which one? Frequency. Understood? Then what the solution for this problem is? First I want to calculate energy. Energy during turn on and turn off. What is energy during turn on? During turn on. Energy during turn on. That is E on. Integral V I dt. That is 0 to T on. Understood? What is the voltage equation during turn on? This is during turn on. Voltage is falling 120 volts to 40 microseconds. Then what is the equation for V? First I want to write. Then this is falling slope now. I told already how to write for falling slope. Then V equal to the voltage equation. What is equation? V equal to amplitude. Amplitude is how much? 120 to 1 minus T by T on. How much? 40 microseconds. That is 40 into 10 to the power of minus 6. Yes. Then you simplify this one. What the expression we can get? What the expression we can get? V equal to 120 into 1 minus 1 by 4 means 0.25 into 10 to the power of 5 into T. Then what is V equal to? 120 into 1 minus 2.5 into 10 power 4 into T. This is equation for V. Then what is the equation for I? You tell me. What is the equation for I? During turn on. What is the equation for I? Then I equal to. Current is rising na? During turn on means current is rising. Current rising means how to write? Amplitude is how much? Amplitude is how much? 80 by. What is turn on time? 50 microseconds. 50 into 10 to the power of minus 6 into T. Then what is I equal to? 1.6 into 10 power 6 into T. This is I. Now, what is the average energy loss during turn on? On state energy loss equal to. Okay. Then integral 0 to. How much on time you take? Here on time is given as 50 microseconds. Here on time is given as 40 microseconds. Which time you can take? The question is asked. The question is asked. Yes, it is given as 40 microseconds. It is given as, sorry, on state turn on time is 40 microseconds. Then it is given as 50 microseconds. Current is rising 50 microseconds. What time you take? You want to calculate for maximum switching frequency. Maximum switching frequency means frequency is high means on and off times are less, because you know that T equal to T on plus T off. That is 1 by F equal to T on plus T off. You want a high frequency means on time and off times must be less. That's why during turn on condition, for turn on is nothing but which one? Voltage is falling up to this one. Okay. This is given as 40 microseconds. During turn on, this is given as how many microseconds? 50 microseconds. You take 40 microseconds or 50 microseconds? Yes, you take 40 microseconds because you want to get the problem is asked on maximum switching rate. You want high frequency means less turn on time and less turn off time you take. Here turn on time is you take 40 into 10 to the power of minus 6 that is V into I into dt. Then on state energy loss E on equal to, you know the V value, you know the I value, substitute these two, then integrate and substitute the limits. Then we can get on state energy loss equal to 51 millijoules. This is on state energy loss. Okay. Now similarly, I want to calculate what is the off state energy loss. You calculate off state energy loss. You calculate off state energy loss. Okay. Note down that one, on state energy loss. This V, you know, substitute here. I, you know, substitute here. Then you can get on state energy loss equal to 51 millijoules we can get. Then you want to calculate similarly off state energy loss. Off state energy loss equal to integral 0 to T off into V into I into dt. Then during off state, you write the expression for V. During off state, you write the expression for V. During off state means voltage is rising. Voltage rising means amplitude is how much? 120 by V by T off. How many microseconds? 75 microseconds into T. This is the expression for V. Okay. Then what is the expression for I? I equal to, current is falling. 80 into 1 minus T is how much? T by T off. T off is how much? 1 by 60 into 10 to the power of minus 6 into T. This is I. Then you substitute V and I here. Then what is the off state energy loss? Off state energy loss equal to, we can get 76.8 millijoules. By substituting this, we can get 76. You substitute V is here and I is here. But before that, one point to remember, integral 0 to, you take 75 microseconds or 60 microseconds. Then you take 60 microseconds. 60 into 10 to the power of minus 6. Because of, you want to get high frequency. Then by substituting V and I, you substitute V and you substitute I here, then what you can get? 76.8 millijoules. 76.8 millijoules. Then what is the total power loss? Total energy loss is how much now? Then total energy loss equal to, that is 51 plus, this is how much? 76.8 millijoules. Okay, this we can get 127.8 millijoules. That is 0.1278 joules. 0.1278 joules. But what is the power equal to? Power equal to how much it is given? 200 watts. Power is given as 200 watts. Then we want maximum switching rate. Then maximum switching rate or frequency. Maximum switching rate or frequency is equal to, how to get that is energy by, you write like this now. How to get maximum switching rate? Power by energy. Power is watts. Energy is watt dash second. Energy is watt dash second. Then you can get watt is how much? Power is how much? 200 watts. This we can get 0.1278 joules. Then we simplify that, we can get how much? 1564.9 cycles or, and frequency na cycles per second. This is cycles per second. 1564 point, that is 15